Right now, our entire galaxy is being dragged through space at nearly 1,400,000 miles per hour, not drifting, not wandering, being pulled. Something massive is hiding behind the Milky Way. We cannot see it. Our own galaxy blocks the view. A wall of dust and gas covers 20% of the visible sky. Astronomers call this region the Zone of Avoidance. Behind it, 250 million light-years away, waits the source of the pull. What if the thing dragging us through the universe is something we have never directly seen? In the last 24 hours, our galaxy traveled 31 million miles toward that hidden destination. The light from whatever is pulling us left before complex life existed on Earth. Yet its gravity reaches us now. It bends our path. It shapes our motion. Early astronomers noticed something strange. Every galaxy in our cosmic neighborhood flows toward the same invisible point. They named the source the Great Attractor. But when they finally pierced the dust with infrared light, what they found was not enough. The mass they measured could not explain the force. Something larger had to be hiding deeper in the dark. We are caught in a river of cosmic matter. Competing gravitational giants pull from ahead. Vast empty voids push from behind. The map of this hidden architecture is still incomplete. If you enjoy what comes next, hit that like button and subscribe. We begin now. The thing blocking our view of the universe is the very galaxy we live in. We are inside the fog, not drifting, not wandering, being pulled, and we cannot even see toward where we are going. Picture yourself standing in a city you have never visited. Every street curves in the same direction. Every gust of wind bends the same way. Every stream flows toward the same hidden place. There is a mountain somewhere ahead of you, massive beyond comprehension. But between you and that mountain sits a wall of fog so thick that no light passes through it. You cannot see the mountain, but you know it exists. Everything around you responds to it. This is our situation in the cosmos. We orbit inside a disk of stars and dust and gas. That disk stretches across the sky like a bright band on clear nights. Beautiful to look at, impossible to look through. The obstruction is not empty space. It is not a void or a gap in the universe. The barrier is made of material, carbon particles smaller than grains of sand, silicates that formed in the death throes of ancient stars, frozen molecules of water and ammonia and methane, drifting between stellar systems for billions of years. These particles hang in the space between our sun and the galactic center. They absorb visible light. They scatter it. They swallow it completely. What reaches our telescopes from that direction is nothing. Darkness. Silence. The dust itself acts like a brick wall made of starlight. It stretches across 1/5 of everything we could ever hope to see. 1/5 of the entire sky, blocked by our own home. For centuries, astronomers worked around this problem by ignoring it entirely. They mapped galaxies to the north. They mapped galaxies to the south. They drew careful charts of cosmic structure in every direction they could see. But across that thick band of obstruction, they simply left their maps blank. They assumed nothing important could be behind it. They assumed the universe was roughly the same in all directions, and whatever was hiding in that stripe was probably just more of what they had already found elsewhere. This assumption was one of the most consequential mistakes in the history of science. Generations of researchers drew maps of the cosmos with a blank stripe running through them. They studied the motions of galaxies above and below that stripe. They noticed something troubling, something that did not fit their models. Galaxies on both sides of the obstruction moved in coordinated ways. They flowed in the same direction. They accelerated toward the same region of space. And it was as if the entire local universe was responding to something hidden behind the wall. Imagine watching leaves blow across a field. They swirl and scatter in random patterns until they reach a certain point. Then, they all curve the same way. They all bend towards something you cannot see. There is a structure there, shaping the flow. You feel its influence in the motion of everything around it. That is what astronomers observed. Galaxies were not drifting randomly. They were flowing. And they were flowing toward the exact region they could not see. Decades passed before technology caught up to the mystery. Infrared light travels through dust more easily than visible light does. The particles that block our eyes cannot block longer wavelengths. In the late 1990s, Yet a survey called 2MASS began mapping the sky in infrared. It penetrated 87% of the obstruction. For the first time, astronomers glimpsed the structures hiding behind our own galaxy. But the deepest 10% remains completely opaque even today. The thickest part of the dust, the region closest to the galactic center, still blocks everything. We have mapped most of the blind spot. We have not mapped all of it. Whatever hides in that final 10% continues to shape our motion. It continues to pull. It continues to bend the paths of 100,000 galaxies, including our own. The fog does not care that we want to see through it. The mountain does not care that we are being dragged toward its slopes. We are passengers inside the very thing that blinds us. And somewhere behind that wall, and the source of the pull, waits in darkness. Astronomers began to notice patterns in the flow. Galaxies on one side of the obstruction moved toward it. Galaxies on the other side moved toward it as well. The motions converged. They pointed to a single region of space, hidden in the thickest part of the dust. Something was there. Something with enough mass to bend the motion of everything nearby. Something that had been shaping our trajectory long before anyone thought to look. The question was no longer whether something massive was hiding behind the Milky Way. The question was how massive, and whether our instruments could ever reveal its true shape. How do you measure the motion of something you are inside of? That was the problem. We live inside the Milky Way. We orbit its center. We spin with it through the void. Every telescope we build, every observation we make happens from within this rotating disk of stars. Measuring our own movement through the universe is like trying to measure the speed of a train while sitting in a windowless car. But there is a way. 380,000 years after the universe began, space cooled enough for light to travel freely. That ancient glow still fills all of space. It comes from every direction. We call it the cosmic microwave background. It is the oldest light in existence, and it provides something extraordinary, a fixed reference frame, a background against which all motion can be measured. Here is the surprise. We did not discover our galaxy's motion by looking at the galaxy itself. We discovered it by reading the temperature of that ancient light. Yet the cosmic microwave background is slightly warmer in one direction and slightly cooler in the opposite direction. This tiny difference, this subtle Doppler shift, reveals that we are moving. We detected our trajectory through the cosmos by measuring the heat signature of creation itself. The numbers tell the story. Our solar system orbits the center of the Milky Way at 515,000 miles per hour. At that speed, you could circle Earth in 3 minutes. That is fast enough to blur the imagination. But this is just our local orbit around the galactic core. It does not tell us where the galaxy itself is going. Astronomers subtracted this orbital motion. They accounted for every known local influence. What remained was a residual velocity, a leftover. Our entire galaxy, along with thousands of others, are moving together in the same direction, moving at roughly 1,300,000 miles per hour relative to that ancient background light. Not random drift, coordinated flow. Imagine standing on a boat in the middle of a river. The current is invisible to you. The water looks perfectly still, but your boat drifts slowly, steadily, in one direction. You are not paddling. The boat simply moves. You look out across the water and notice other boats scattered around you. They are drifting too, all of them, all moving the same way, all being carried by the same invisible current toward the same unseen destination. That is what astronomers found when they mapped the motions of galaxies in our cosmic neighborhood. 1,300,000 miles per hour. What does that feel like? In a single day, our galaxy travels farther than any human spacecraft has ever gone. In 1 year, we cross 11 billion miles, not toward some random patch of sky, toward a specific region, toward the exact place hidden behind our own galaxy's dust. When researchers plotted the flow lines, they converged. The motion of our galaxy pointed one way. The motion of our neighbors pointed the same way. The motion of galaxies above and below the plane of dust pointed there too. Everything nearby was participating in the same gravitational current. What exactly sits at the center of this flow? That was the question. And for years, the honest answer was, we have no idea. We could feel the pull. We could measure it. We just could not see what was doing the pulling. The evidence was indirect but undeniable. Velocity measurements, Doppler shifts, careful calculations of how fast things moved and in what direction. Every analysis pointed to the same conclusion. Something massive lurked in that blind spot. Something with enough gravitational influence to redirect the paths of entire galaxies. Something anchoring the flow of everything in our region of space. Astronomers gave it a name. They called it the Great Attractor. Not because they understood it, not because they had seen it, but because they needed a word for the thing that was pulling us. The name captured the mystery. Here was an invisible gravitational anchor, powerful enough to affect 100,000 galaxies, hidden behind the thickest part of our own galactic disk. For decades, that name was all we had, a label for something we could feel, but not see. A destination we were approaching at speeds almost too large to comprehend. The Great Attractor sat in darkness, bending trajectories, shaping the architecture of our local universe, while we measured its influence from the outside and wondered what it truly was. The flow continued, the pull persisted, and somewhere behind that wall of dust and starlight, the source waited to be revealed. Scientists began developing new tools. They needed eyes that could see through the obstruction. They needed light that dust could not stop. The eyes we needed already existed. We had simply been using the wrong ones. For centuries, astronomers relied on visible light, the same wavelengths your eyes detect right now. Blue skies, red sunsets, the white glow of distant stars. This was our window into the cosmos, and it worked beautifully. Until we tried to look through our own galaxy. Visible light cannot penetrate the zone of avoidance. Those particles of carbon and frozen molecules absorb it completely. Optical telescopes pointed at that region see nothing but a dark stripe across the sky. The information is there. The galaxies are there. The light simply cannot reach us. But light comes in many forms. Infrared radiation has longer wavelengths than visible light, much longer. Where blue light might be absorbed by a dust grain, infrared can slip past it. The particle is still there, but the longer wave bends around it, continues on, reaches our detectors. Consider searching for someone trapped in a building filled with thick smoke. Visible light scatters off the smoke particles. You see grey haze, nothing more. Switch to thermal imaging, and suddenly the heat signature of what you are looking for appears. The smoke has not vanished. Your eyes simply learn to see through it. That is what infrared astronomy offered, a way to detect the heat signatures of distant galaxies even when their visible light was completely blocked. Radio waves pushed even further. At a wavelength of 21 centimeters, neutral hydrogen atoms emit a distinctive signal. This is the building block of galaxies, scattered throughout the universe in enormous clouds. Radio telescopes tuned to this frequency could detect hydrogen concentrations hiding behind the dust. They could map structure that visible light would never reveal. The combination was transformative. Infrared surveys began scanning the zone of avoidance systematically. Yet where optical maps showed emptiness, these new observations revealed thousands of previously hidden galaxies. The blank stripe on our cosmic maps started filling in, point by point, galaxy by galaxy. The fog was finally lifting. What emerged was not random scatter. Behind that wall of dust and starlight, astronomers found exactly what the gravitational mathematics had predicted: a massive concentration of galaxies, thousands of them, packed into a relatively small region of space, sitting precisely where the flow lines of our cosmic neighborhood converged. They called it the Norma Cluster, 220 million light-years away. The distance alone deserves a moment of stillness. Light travels at roughly 670 million miles per hour. Nothing in the universe moves faster. At that speed, you could circle Earth nearly 8 times in a single second. And yet, light leaving the Norma Cluster takes 220 million years to reach us. The photons arriving at our telescopes tonight began their journey before dinosaurs walked the Earth, before the first flowering plants appeared, before anything with eyes existed on this planet. When that light started traveling, complex animal life had barely begun to develop. The Cambrian explosion was still in the future. For 220 million years, that light crossed the void between galaxies. It passed through intergalactic space so empty that a cubic meter might contain only a single atom. It traveled while continents drifted, while mass extinctions reshaped life on Earth 5 separate times, as while mammals evolved from tiny nocturnal creatures into creatures capable of building radio telescopes. And here is what stops me cold. While that ancient light was traveling toward us, the gravity from its source was already reaching across the same distance. Gravity propagates at the speed of light, but the Norma cluster has existed for billions of years. Its gravitational influence arrived here long before its first photons did. The pull was shaping our trajectory, while the light was still in transit. The destination was bending our path before we could see where we were going. We found it. The thing doing the pulling, the source of the flow. It was real. It was there, and it had been hiding in our cosmic backyard the entire time. Yet the Norma cluster sits in a region where the density of matter reaches 10,000 times the average density of the universe. Picture the difference between a single drop of water suspended in a swimming pool and that same drop concentrated into a space smaller than a pinhead. The contrast is similar. Most of space is almost perfectly empty. Norma is packed with galaxies so tightly that they interact constantly, collide frequently, tear each other apart. This was one of the most massive structures within a billion light-years of Earth. It was not lurking at the edge of the observable universe. It was not hidden in some exotic corner of the cosmos, requiring decades of dedicated observation. It was right there, behind a band of dust less than 100,000 light-years thick. Our own galaxy, almost a mere 100,000 light-years across, had blocked our view of something this enormous. The veil had been so thin, the prize behind it so vast. Astronomers felt the rush of confirmation. The great attractor had a face. The mathematics had been vindicated. Decades of indirect measurement, of velocity analysis, of careful inference about unseen mass, had all pointed to this location. And when technology finally allowed us to look, there it was. Thousands of galaxies bound together by mutual gravity. A cosmic city of unimaginable scale. The anchor point of our local flow. The discovery felt like a conclusion. The mystery of the great attractor seemed solved. We had named the thing pulling us, then found it, then measured it. But when astronomers calculated the total mass of what they had found, something was wrong. And the math was supposed to work. When astronomers finally penetrated the dust and found the Norma cluster sitting exactly where their calculations predicted, they expected the numbers to add up. They had spent decades measuring velocities, tracking the peculiar motions of galaxies across the local universe, building models of gravitational influence. The discovery of Norma should have been the final piece of a completed puzzle. It wasn't. They began tallying the mass, galaxy by galaxy, counting the luminous matter, estimating the dark matter halos surrounding each collection of stars, adding up the total gravitational weight of everything visible within the cluster. The calculations took months. The results came back troubling. The Norma cluster was massive. That much was undeniable. But it was not massive enough. And here is the problem. Gravity works in predictable ways. If you know how fast something is moving, and you know the direction of that movement, you can work backward to calculate how much mass must be pulling on it. The equations are straightforward. Newton figured out the basic principles 3 centuries ago. Einstein refined them. The math is reliable. Astronomers had already measured the velocity field. They knew how fast galaxies were moving toward the great attractor region. They knew the direction. They knew the scale of the flow. Hundreds of thousands of galaxies across hundreds of millions of light years were all being dragged in the same general direction. For that kind of influence, you need an extraordinary amount of mass. The Norma cluster contained thousands of galaxies. Each galaxy contained billions of stars. Each star system was surrounded by planets, dust, gas, and invisible dark matter. The total mass was staggering by any human standard. Yet when astronomers plugged that mass into their equations, the numbers fell short, dramatically short. Not a few galaxies, not dozens, thousands of galaxies in Norma alone, and still not enough. The gravitational pull they had measured was too strong. The velocity field was too broad. The influence extended too far. Norma could account for part of the attraction, certainly, but something else had to be contributing, something with far more gravitational weight than what they had found. Picture throwing a bowling ball into a calm lake. The impact creates ripples spreading outward in all directions. If you measure those ripples carefully, you can estimate the weight of the ball that created them, and the size of the waves, the speed at which they travel, the distance they spread before fading. All of this tells you something about the original impact. If the ripples were too large for the ball you threw, you would have a problem. If they spread too far, too fast, reaching distances that a bowling ball simply could not explain, you would be forced to conclude that something else hit the water, something you did not see, something heavier than what you were looking at. That was the situation astronomers faced. The ripples in the cosmic velocity field were too large for the ball they had found. The gravitational waves spreading across the local universe demanded more mass than Norma could provide. The cluster was real. The pull was real. But there was a mismatch between cause and effect that could not be ignored. Finding Norma and realizing it was not enough was like discovering the engine of a speeding car and finding it was too small. You measure the vehicle traveling at tremendous velocity. You open the hood expecting to find an engine capable of producing that speed. Instead, you find something modest, something that might push the car at half the measured pace. The conclusion is unavoidable. There must be a second engine hidden somewhere, something you have not located yet. So the Great Attractor was pulling on approximately 100,000 galaxies. That number deserves emphasis, not a few hundred, not a few thousand. 100,000 separate galaxies, each containing billions of stars, all being tugged in the same direction across spans of hundreds of millions of light years. The gravitational reach was enormous. The influence was cosmic in scale. For that kind of power, you need more than a single cluster, even a dense, violent, active cluster like Norma. This was the moment the mystery deepened rather than resolved. Scientists had expected to find an answer behind the Zone of Avoidance. They had expected to name the thing pulling us and close the chapter on decades of speculation. Instead, they found a piece of the answer, a significant piece certainly, but clearly incomplete. The discovery raised an uncomfortable question. If Norma was not the full explanation, what else was back there? What additional mass was hiding in the cosmic darkness, contributing to a gravitational pull that exceeded what the visible structures could produce? The dust had been pierced. The cluster had been found. The face of the Great Attractor had been revealed. And yet, the fundamental mystery remained intact. Something larger was operating. Something beyond what even the newly unveiled Norma cluster could account for. Astronomers realized they had made a conceptual error. They had been thinking of the Great Attractor as a single object, a destination, a point on a map that they could identify and label and comprehend. That model was too simple. The gravitational field they were measuring did not have a single source, and it had multiple contributors, overlapping influences, structures nested within structures, each adding its weight to the cosmic pull. The Norma cluster was not the answer. It was the beginning of a deeper investigation. The mass deficit pointed towards something more vast than a cluster, something that would require entirely new surveys, new instruments, a fundamental reimagining of what was hiding behind our galaxy's obscuring band of dust. The solution had revealed a bigger problem. The face of the Great Attractor was real, but it was only one face among many, and the others remained hidden in the dark. The others remained hidden in the dark. But what exactly was hiding? That question needed an answer, and the answer required a different way of thinking. Actually, I should be more careful here. When I say the Great Attractor, it sounds like I am naming a thing, a specific object you could point to, but that is not quite right. The Great Attractor is better understood as a direction, a gravitational address. It is not a noun. It is closer to a verb. The act of attracting, spread across an enormous region of space. Astronomers began correcting their own language. They stopped calling it an object. They started calling it a zone, a region, a concentration. The shift in vocabulary mattered. It reflected a fundamental change in understanding. The Great Attractor was never a destination you could arrive at. It was a territory you were already passing through. Deeper mapping revealed the truth. Behind the dust, there was not one cluster pulling on everything. There was a vast collection of clusters, interconnected, overlapping, and their gravitational fields merging into a single regional force. Each cluster contributed its own pull. Together, they created something far more powerful than any single structure could produce. Think of a mountain range, not a single peak, but dozens of summits rising together across a span of geography. No individual mountain is responsible for the way rivers form in that region. No single summit dictates where valleys cut through the landscape. The entire range, working together, shapes the terrain for hundreds of miles in every direction. Water flows, rock erodes, everything responds to the collective presence of all those peaks combined. The Great Attractor is the gravitational equivalent of that range. We had been searching for a single summit, a solitary mountain so massive it could explain everything. Yet that mountain did not exist. Instead, there was a ridge, a chain, a territory of elevated mass stretching across hundreds of millions of light years. Consider how this changes the picture. A single object pulls from a single point. You can calculate its location. You can measure your distance from it. You can predict your trajectory toward it with relative simplicity. A region is different. A region has no center, or rather, its center is an average, a mathematical midpoint that may contain nothing special at all. The heart of this concentration sits roughly 250 million light-years from where you are lying right now. That distance would take light itself over 250 million years to cross. If you somehow launched a spacecraft today traveling at the speed of our fastest probes, you would need roughly 4 trillion years to arrive. The universe itself is only 14 billion years old. The journey would take nearly 300 times longer than everything that has ever existed. And when you arrived, you would not find a single object waiting for you. You would find yourself surrounded, clusters in every direction, dense regions of matter pulling from multiple angles. The gravitational field you had been traveling toward would be all around you, not in front of you. Here is where the conceptual error becomes clear. We assumed gravity works like a spotlight, a beam of force emanating from one bright source. Point at the source, measure its strength, calculate its effect. But gravity does not operate that way across cosmic scales. It works more like a pressure gradient. Yes, as the entire region pushes and pulls based on the cumulative distribution of mass across vast volumes of space. There is no great attractor object. There is only the great attractor region. The density of this region helps explain that was the situation astronomers faced. The ripples in the cosmic velocity field were too large for the ball they had found. The gravitational waves spreading across the local universe demanded more mass than Norma could provide. The cluster was real. The pull was real. But there was a mismatch between cause and effect that could not be ignored. Finding Norma and realizing it was not enough was like discovering the engine of a speeding car and finding it was too small. You measure the vehicle traveling at tremendous velocity. You open the hood expecting to find an engine capable of producing that speed. Instead, you find something modest, something that might push the car at half the measured pace. The conclusion is unavoidable. There must be a second engine hidden somewhere, something you have not located yet. So the Great Attractor was pulling on approximately 100,000 galaxies. That number deserves emphasis, not a few hundred, not a few thousand. 100,000 separate galaxies, each containing billions of stars, all being tugged in the same direction across spans of hundreds of millions of light years. The gravitational reach was enormous. The influence was cosmic in scale. For that kind of power, you need more than a single cluster, even a dense, violent, active cluster like Norma. This was the moment the mystery deepened rather than resolved. Scientists had expected to find an answer behind the Zone of Avoidance. They had expected to name the thing pulling us and close the chapter on decades of speculation. Instead, they found a piece of the answer, a significant piece certainly, but clearly incomplete. The discovery raised an uncomfortable question. If Norma was not the full explanation, what else was back there? What additional mass was hiding in the cosmic darkness, contributing to a gravitational pull that exceeded what the visible structures could produce? The dust had been pierced. The cluster had been found. The face of the Great Attractor had been revealed. And yet, the fundamental mystery remained intact. Something larger was operating. Something beyond what even the newly unveiled Norma cluster could account for. Astronomers realized they had made a conceptual error. They had been thinking of the Great Attractor as a single object, a destination, a point on a map that they could identify and label and comprehend. That model was too simple. The gravitational field they were measuring did not have a single source, yet it had multiple contributors, overlapping influences, structures nested within structures, each adding its weight to the cosmic pull. The Norma cluster was not the answer. It was the beginning of a deeper investigation. The mass deficit pointed towards something more vast than a cluster, something that would require entirely new surveys, new instruments, a fundamental reimagining of what was hiding behind our galaxy's obscuring band of dust. The solution had revealed a bigger problem. The face of the Great Attractor was real, but it was only one face among many, and the others remained hidden in the dark. The others remained hidden in the dark. But what exactly was hiding? That question needed an answer, and the answer required a different way of thinking. Actually, I should be more careful here. When I say the Great Attractor, it sounds like I am naming a thing, a specific object you could point to, but that is not quite right. The Great Attractor is better understood as a direction, a gravitational address. It is not a noun, it is closer to a verb. The act of attracting, spread across an enormous region of space. Astronomers began correcting their own language. They stopped calling it an object. They started calling it a zone, a region, a concentration. The shift in vocabulary mattered. It reflected a fundamental change in understanding. The Great Attractor was never a destination you could arrive at. It was a territory you were already passing through. Deeper mapping revealed the truth. Behind the dust, there was not one cluster pulling on everything. There was a vast collection of clusters, interconnected, overlapping, and their gravitational fields merging into a single regional force. Each cluster contributed its own pull. Together, they created something far more powerful than any single structure could produce. Think of a mountain range, not a single peak, but dozens of summits rising together across a span of geography. No individual mountain is responsible for the way rivers form in that region. No single summit dictates where valleys cut through the landscape. The entire range, working together, shapes the terrain for hundreds of miles in every direction. Water flows, rock erodes, everything responds to the collective presence of all those peaks combined. The Great Attractor is the gravitational equivalent of that range. We had been searching for a single summit, a solitary mountain so massive it could explain everything. Yet that mountain did not exist. Instead, there was a ridge, a chain, a territory of elevated mass stretching across hundreds of millions of light years. Consider how this changes the picture. A single object pulls from a single point. You can calculate its location. You can measure your distance from it. You can predict your trajectory toward it with relative simplicity. A region is different. A region has no center, or rather, its center is an average, a mathematical midpoint that may contain nothing special at all. The heart of this concentration sits roughly 250 million light-years from where you are lying right now. That distance would take light itself over 250 million years to cross. If you somehow launched a spacecraft today traveling at the speed of our fastest probes, yet you would need roughly 4 trillion years to arrive. The universe itself is only 14 billion years old. The journey would take nearly 300 times longer than everything that has ever existed. And when you arrived, you would not find a single object waiting for you. You would find yourself surrounded, clusters in every direction, dense regions of matter pulling from multiple angles. The gravitational field you had been traveling toward would be all around you, not in front of you. Here is where the conceptual error becomes clear. We assumed gravity works like a spotlight, a beam of force emanating from one bright source. Point at the source, measure its strength, calculate its effect. But gravity does not operate that way across cosmic scales. It works more like a pressure gradient. As the entire region pushes and pulls based on the cumulative distribution of mass across vast volumes of space. There is no Great Attractor object. There is only the Great Attractor region. The density of this region helps explain its power. The matter concentrated here is 10,000 times denser than the average density of space. Picture taking all the material scattered across a typical section of the universe, a section containing almost nothing but empty void, and compressing it down by a factor of 10,000. That is what this region achieved through billions of years of gravitational collapse. Matter falling toward matter, clusters forming near other clusters, everything drawing tighter and tighter into a regional knot. This knot exerts its influence across staggering distances. Roughly 100,000 separate galaxies respond to its pull. Each of those galaxies contains billions of stars. Each of those stars may host its own system of worlds. The scale of what is being influenced defies any metaphor that fits inside a human mind. And here is what makes this reframe so important. Understanding the Great Attractor as a region, rather than an object, changed what astronomers were looking for. They stopped searching for a single explanation. They started mapping relationships, connections between clusters, flow patterns through the cosmic web, the way structures group together into larger structures, which group together into still larger structures. The region does not exist in isolation. It sits at the center of something even more vast, a superstructure that contains our galaxy, our local group, our nearest neighbors, and everything we have ever observed with unaided eyes. The Great Attractor is not the final answer. It is the gravitational core of a much larger system we belong to. That system has a name, but not yet. For now, what matters is the shift in perspective. We are not falling toward a thing. We are caught in a basin, a gravitational valley carved by the collective mass of countless clusters working in concert. Rivers do not flow toward a single point. They flow toward the lowest ground. The Great Attractor region is the lowest ground in our corner of the universe. Everything nearby is slowly draining toward it. Our galaxy is one small stream in that cosmic watershed. Inside this region, conditions are extreme. Galaxies do not drift peacefully. They collide. They merge. They are stripped of their outer layers by the intense gravitational forces. Stars are ripped from their homes. Gas is heated to millions of degrees. The region is not just massive. It is violent. A factory of destruction operating across scales almost too large to measure. One galaxy in particular tells the story of what happens when you fall into this basin. Its gas trails behind it like a blue ribbon, stretched across 200,000 light-years of space. It is being torn apart, consumed by the very region it was pulled into. That galaxy deserves a closer look. Its name is ESO 137-001. Astronomers call it the Jellyfish Galaxy. The name is not poetic exaggeration. It describes exactly what this galaxy looks like, a body with long trailing tentacles streaming behind it. Except the body is made of 100 billion stars, and the tentacles are made of gas being ripped away into the void. This galaxy is falling. Not falling the way a stone falls. Falling the way a creature falls into something that will consume it. Slowly, relentlessly, without any possibility of escape. The Jellyfish Galaxy sits inside the Norma cluster, the heart of the region we have been circling toward. It is one of the most visible galaxies there, and it is dying. The death is not violent in the way we usually imagine cosmic violence. There is no explosion, no collision, no sudden catastrophe. Instead, the galaxy is being stripped, peeled. Its outer layers are being torn away by something it cannot outrun. The process has a clinical name: ram pressure stripping. The words sound technical, almost sterile, but what they describe is brutal. Picture a swimmer moving through thick water. Their hair streams behind them as they push forward. That image makes sense. We understand resistance. We understand drag. Now imagine the water is not just thick. It is so dense, so resistant, that it does not simply trail the swimmer's hair behind them. It tears the hair out, strand by strand. The faster the swimmer moves, the more they lose. That is what is happening to the Jellyfish Galaxy. The space between galaxies is not truly empty. It contains a thin haze of gas, mostly hydrogen, heated to extraordinary temperatures. This is the intergalactic medium. In most places, it is so sparse that it barely exists. A few particles scattered across cubic meters of nothing. But inside a cluster like Norma, the intergalactic medium is different. Denser, hotter, millions of degrees. A galaxy falling into this environment encounters resistance. Not the kind of resistance you can see, not a wall or a surface, just pressure. Constant, invisible pressure pushing against everything the galaxy carries with it. The stars survive. They are too compact, too dense to be affected. They continue their orbits as if nothing is happening. But the gas does not survive. Galaxies carry enormous clouds of gas within them. This gas is their fuel, their future. Without it, no new stars can form. The gas is what allows a galaxy to renew itself, to create the next generation of suns, to remain alive in any meaningful sense. The intergalactic medium pushes against this gas like wind against a wet cloth, and the gas is torn away. Behind the Jellyfish Galaxy, as a tail stretches across an almost incomprehensible distance, 200,000 light-years of stolen material streaming into the void. That is twice the width of our entire galaxy, a river of gas longer than anything in our local neighborhood. The tail glows blue in ultraviolet images. That color is significant. Blue light comes from young stars, hot stars, stars that formed recently. Here is the strange truth at the heart of this destruction. The process that is killing the jellyfish galaxy is also triggering new creation. As the gas is stripped away, it compresses. Pockets of material are squeezed together by the very forces tearing them loose. And in those compressed pockets, gravity takes over. The gas collapses, ignites, becomes stars. New stars are being born in the tail of a dying galaxy. They blaze blue and bright, young suns forming in the wake of catastrophe. Born not inside a galaxy, but in the empty space between giants. They will never orbit a galactic core. They will never belong to any structure we would recognize. They are orphans, created by destruction, destined to drift alone through the void forever. The jellyfish galaxy is like a comet, but instead of ice and rock, forces are in competition, and the outcome is a balance of forces that is simultaneously contracting at its center and being ripped apart at its boundaries, pulled inward and torn outward at the same time. The forces are in competition, and the outcome depends on where you stand. For now, the Milky Way is deep enough inside Laniakea that gravity dominates. We are falling toward the center. We will continue falling for billions of years. The journey will not end in our lifetime, or in the lifetime of our sun, or in the lifetime of most stars burning today. But the discovery of Laniakea did more than give us a name for our home. It gave scientists a framework, a map with boundaries, a way to calculate how much mass exists inside those boundaries and how that mass should affect our motion. They ran the numbers. They added up the galaxies. They estimated the dark matter threading through the structure. They calculated how fast we should be moving based on everything Laniakea contains. And the numbers did not match. The pull was too strong. The velocity was too high. Something was still missing from the equation. Something beyond the edges of the map. Something outside Laniakea, reaching across the void, adding its own gravity to the flow. The immeasurable heaven was not the end of the story. In 2014, an astronomer named Renee Kran-Korteweg was hunting for something she suspected was there. For years, she had studied the motion of galaxies near the thickest part of the dust wall, the part that swallowed light completely, the part where every previous survey had simply given up. She was not looking at visible light. She was not even using the same infrared techniques that had mapped most of the hidden sky. She was pushing deeper, using specialized observations that could penetrate regions others had written off as impossible. And she found something. Behind the densest curtain of dust in our entire sky, hidden by the spray of 100 billion stars, sat a structure no one had ever seen. A supercluster. Massive, ancient, completely unknown to science. She named it Vela, after the constellation that concealed it. Vela sits approximately 800 million light-years from Earth. That distance is difficult to hold in your mind. Light itself, traveling at the fastest speed the universe allows, would need 800 million years to make the journey. And the light arriving from Vela tonight left its galaxies before complex life existed on our planet. But the distance is not the remarkable part. Vela stretches 300 million light-years across. That is wider than the distance from here to the Great Attractor. A single structure spanning a gulf so vast that if you could somehow travel from one edge to the other at the speed of light, 10 generations of stars would be born and die before you arrived. And the mass. Vela contains at least 1,000 times the mass of our entire galaxy. Not in a single object, not even in a single cluster, but in a sprawling archipelago of galaxy clusters, each one containing thousands of galaxies, each galaxy containing billions of stars, all of it pulling on everything around it, all of it bending the fabric of space, or all of it completely invisible until 11 years ago. Finding Vela was like discovering a second waterfall behind the one you thought was making all the noise. Imagine you have spent decades standing at the base of a great cascade. You have measured the mist. You have calculated the flow. You have built instruments to map where every droplet lands. And you were certain, absolutely certain, you understood where all the water was going. Then you walked around a corner, and you found another waterfall twice as tall, hidden by the spray of the first. That is what happened in 2014. For years, astronomers had assumed The Great Attractor region was the primary engine pulling our galaxy through space. They had calculated the mass. They had mapped the galaxies they could see. It was running the entire time. Accelerating was running the entire time. Accelerating thousands of galaxies, bending the flow of matter across hundreds of millions of light years. And nobody knew it existed. This is the part that gets me. We have telescopes that can see galaxies 13 billion light years away. We have mapped millions of galaxies across the observable universe. And yet, in 2014, we found something 1,000 times heavier than our own galaxy, sitting less than 1 billion light years away, that nobody knew existed. The universe is still hiding things from us. Right behind our own backyard, something massive is hiding behind the Milky Way. Yes, but the word hiding suggests intent. It suggests the universe is keeping secrets on purpose. That is not quite right. The universe is not hiding anything. We are simply standing in a bad spot. Our view is blocked by the very galaxy that gives us life. The dust that obscures Vela is made of the same elements that built our bones. We are blind to what lies in certain directions because of where we happen to be, and that blindness lasted until the technology and the determination finally caught up. Kran Korteweg spent years pushing into territory that other surveys avoided. She knew something had to be there. The motions of nearby galaxies did not make sense otherwise. The pull was too strong. The velocity field was wrong. She was right. The discovery of Vela forced scientists to redraw their maps, and not just the maps of what exists in that region, but the maps of where everything is going. The flow of matter through our cosmic neighborhood suddenly had a second source, a second attractor, a second hand on the steering wheel. Think about what this means for our understanding. Every model of local motion had been missing a piece. Every calculation of why we move the way we do had been operating with incomplete data for decades, and Vela was not a small correction. This was not a minor adjustment to the math. This was a structure containing enough mass to pull galaxies across a significant fraction of the observable universe. It had been there for billions of years, shaping the paths of everything nearby, and we simply could not see it. The year matters, 2014, not a century ago, and not before computers or satellites or modern astronomy. This happened after we had landed robots on Mars, after we had photographed galaxies at the edge of the observable universe, after we had built telescopes the size of buildings and launched observatories into orbit around the sun. And still, something this large remained hidden. If we missed Vela until 11 years ago, what else is back there? What other structures are lurking in the deepest parts of the dust, shaping the motion of galaxies, bending the trajectories of everything we can see? The honest answer is we do not know. The zone of avoidance still holds secrets. The thickest regions, the parts closest to the heart of our own galaxy, remain difficult to penetrate, even with our best instruments. Every few years, as a new technique reveals something that was previously invisible, every few years the map gets redrawn. Vela was a reminder, a humbling one. The universe does not arrange itself for our convenience. It does not place its largest structures where they are easy to observe. It simply exists, vast and indifferent, and we catch glimpses when we can. But the discovery also raised a troubling question. If our galaxy is being pulled by the Great Attractor and Vela simultaneously, if there are multiple engines tugging us in slightly different directions, then the picture of our motion becomes more complicated. It is no longer a simple flow toward a single destination. It is a compromise between competing forces. And there was something else the scientists were beginning to notice. In something that did not fit the pattern of attraction at all. The pull was real. Multiple sources had been confirmed, but the numbers still did not quite add up. We were moving as if something else was involved, something that was not pulling us forward at all, something that was pushing us from behind. Turn around, face the opposite direction, point away from the Great Attractor, away from Vela, away from everything that has been pulling us forward. Look at what sits on the other side of the sky. Nothing. That is not a figure of speech. On the exact opposite end of our cosmic trajectory, astronomers found one of the emptiest regions of space ever measured. A vast hollow expanse containing almost no galaxies, almost no clusters, almost no matter at all. They named it the dipole repeller. The name is strange. Voids do not push. They cannot reach out and shove matter away. They have no mechanism to propel anything. Emptiness does not exert force. And yet, this void is doing something. It is contributing to our motion just as powerfully as the attractors ahead of us. Here is how it works. Gravity pulls. We know this. Mass attracts mass. The more matter in a region, the stronger the gravitational pull toward it. This is the physics that drags us toward the great attractor, toward Vela, toward every concentration of galaxies we have discussed. But consider what happens in a region with almost no mass. The gravitational pull from that direction becomes weak, almost absent. Meanwhile, the regions around it, filled with normal amounts of matter, pull with normal strength. The imbalance creates motion. It looks exactly like pushing. Picture looks exactly like pushing. Picture yourself standing in a doorway. On one side of you, an open door leads to a calm room. On the other side, someone has placed a vacuum cleaner at full power. The open door does not push you. It simply lets air flow through. The vacuum sucks air toward it. You feel yourself drawn in that direction. Now stand in the middle. The calm side offers no force in either direction. The vacuum side pulls. The result is that you move toward the vacuum. But here is the strange part. If you did not know about the vacuum, if you could only feel the motion and not see the cause, yet you might conclude that the calm room was pushing you. Something on that side seems to be forcing you away. That is what the dipole repeller does to our galaxy. It sits behind us, vast and hollow. Its gravitational influence is close to zero. Ahead of us, the great attractor and Vela and every other concentration of matter tug with enormous force. The contrast between the pulling ahead and the absence behind creates our trajectory. We are not just falling towards something. We are falling away from nothing. The physics here deserves a moment. Gravity, we typically assume, is a purely attractive force. Things with mass pull on other things with mass. Period. But in a universe with uneven distribution of matter, with dense regions and empty regions scattered across billions of light years, in that attraction creates something more complex. The flow of galaxies becomes directional. Matter streams away from voids and collects in walls and filaments and clusters. The absence of mass in one direction is functionally equivalent to an extra push from that direction. Emptiness has power. Nothing is doing something. The dipole repeller stretches across hundreds of millions of light years. Its boundaries are difficult to map precisely because there is so little inside it to observe. You cannot photograph emptiness. You can only infer it by measuring what surrounds it and noticing the gap. Astronomers traced its outline by watching how galaxies moved at its edges, how the velocity field warped around its borders. What they found changed the equation entirely. For decades, scientists had tried to explain our motion using attraction alone. The great attractor was discovered, then Vela, then the larger structures beyond them. Each discovery added another pulling force to the model, and each time, the numbers still fell short. The velocity was too high. We were moving faster than the attractors could explain. The dipole repeller solved the discrepancy. When astronomers added its influence to their calculations, the math finally balanced. The void behind us contributes roughly half of our peculiar velocity. Half, an entire engine of motion, just as powerful as all the attractors combined, and it is made of nothing. Consider a river. Water flows from high ground to low ground. We understand that intuitively, but imagine a river flowing between two valleys, one full and one empty. And the water does not just fall into the lower valley, it also drains away from the empty one. The absence of water in the dry valley creates an imbalance that accelerates the flow. The river moves faster because something is missing. We are that river. The attractors are the lower valley. The dipole repeller is the dry basin behind us. Our galaxy moves through space at over 1 million miles per hour, a staggering velocity. But without the void behind us, we would be moving at roughly half that speed. The pull from ahead would still exist. The great attractor would still tug. Vela would still contribute. But the motion would be slower, gentler. The void doubles our pace. This is not metaphor. This is measured physics. In 2017, a team of researchers published the first detailed map of the dipole repeller. They traced its boundaries, calculated its contribution to local motion, and confirmed that our velocity is the product of two forces working together, pulled from ahead, released from behind. Both matter equally. Sit with that for a moment. Every time you look at the night sky, Half the reason you are moving is because of something that is not there, an absence shaping your trajectory just as profoundly as a presence. The things we cannot see because they do not exist are pushing us through the universe. The dual-engine model makes sense now. Attractors ahead, repeller behind, both contributing, both essential. But even this picture is incomplete. The scientists who drew the velocity maps noticed something else. Another anomaly, another force they could not fully explain with the structures they had found, is somewhere beyond the Great Attractor, beyond Vela, beyond the local attractors we had catalogued. Something else was pulling, something enormous, and it sat at twice the distance we had been mapping, exerting influence that rivaled everything closer combined. Something enormous sat at twice the distance we had mapped. That phrase lingered in the data. Twice the distance. Scientists had charted the Great Attractor. They had found Vela lurking in the dust. They had measured the void pushing from behind. And still, the equations pointed somewhere deeper, somewhere farther, somewhere they had not yet looked carefully enough. 650 million light-years away, there is a Titan. Let that distance settle. Light traveling at the fastest speed the universe allows, crossing the emptiness between stars. Passing galaxy after galaxy would need 650 million years to reach us from this place. When that light began its journey, the most complex life on Earth was single-celled. No eyes existed to see, no brains existed to wonder. The light traveled through a universe that had never known thought, and it arrived here tonight, carrying information about something that dwarfs everything else we have discussed. This is the Shapley supercluster. You might expect that something twice as far away would pull half as hard. That is how distance usually works. Double the gap, quarter the force. The math of gravity is unforgiving that way. A magnet across the room barely tugs at a paperclip. Move it to the next building, and the pull vanishes entirely. Shapley breaks that expectation. And it sits at twice the distance to the Great Attractor. Yet it pulls on our cosmic neighborhood with roughly equal strength. How is that possible? There is only one answer. It must be far, far more massive. So massive that the extra distance becomes almost irrelevant. So massive that its gravitational reach extends across 650 million light-years and still arrives with enough force to compete with structures half as far away. Imagine a bonfire and a distant sun. Stand close to the bonfire, and you feel its heat on your face. The sun is millions of times farther, yet its warmth still reaches you. Why? Because the sun is not just bigger, it is incomprehensibly bigger. It overwhelms distance with sheer scale. Shapley is the gravitational sun to the Great Attractor's bonfire. The numbers here require patience, yet they are too large to grasp without translation. Shapley contains more than 30 galaxy clusters. Not galaxies, clusters of galaxies. Each cluster holds hundreds or thousands of individual galaxies. Each galaxy holds billions of stars. The nesting goes deeper than intuition can follow. In its densest regions, Shapley contains more than 8,000 individual galaxies. Picture the Milky Way, 200 billion stars bound together in a spiral disk spanning 100,000 light-years. That is one galaxy. Shapley holds 8,000 of them packed into its core alone, and that is only the densest part. The total mass of the Shapley supercluster exceeds 10 million billion times the mass of our Sun. Written out, that number requires 16 digits, 10 followed by 15 zeros. A quantity so vast that the human mind slides off it like water off glass. Here is another way to understand it. If you converted Shapley's total mass into Milky Way galaxies, you would have 10 million of them. 10 million galaxies worth of matter, not spread across the entire universe, concentrated in one region, pulling on everything within a billion light-years. We did not fully understand its influence until the 21st century. Astronomers had known about Shapley for decades. They had catalogued its clusters. They had measured the distances to its brightest galaxies. But the realization that it was actively shaping our motion, competing with the Great Attractor to determine our trajectory through space, came later, much later. Only when the velocity maps grew precise enough, or only when we could trace the flow of galaxies across hundreds of millions of light-years, did the picture clarify. The Great Attractor and Shapley are not separate destinations. They are two anchor points on the same gravitational rope. Consider a ship being pulled toward shore. One line is tied to a dock close by. Another line is tied to a crane much farther down the beach. Both lines are taut. Both are pulling. The ship does not move toward just one. It moves along the combined direction of both forces. The local universe is that ship. The great attractor is the closer dock. Shapley is the distant crane. Both are pulling the local universe toward the southern sky. Not slowly, not gradually, over billions of years. Right now, this motion is happening. At the heart of Shapley sits a structure called Abell 3558. It is one of the densest concentrations of matter in the known universe. Galaxies there crowd together at separations that would seem claustrophobic by cosmic standards. The gravitational field in that region is a pit so deep that light itself bends as it passes through. Space curves inward around all that mass, funneling everything nearby toward the center. If the great attractor is a hand gripping your shirt, Shapley is a tractor pulling a chain attached to your belt. One is closer, one is stronger. Both are moving you the same direction. The discovery of Shapley's true influence forced astronomers to redraw their mental maps. The great attractor had seemed like the final answer, the source of our motion, the hidden mountain behind the fog. But mountains can have larger mountains behind them. The horizon can recede. What you thought was the edge of the world turns out to be a ridge, with a vastness beyond it you had not imagined. Everything we have described so far fits inside a volume of space less than 1 billion light-years across. The Norma cluster, the great attractor region, Vela, Laniakea, Shapley. All of them are nodes in the same web. All of them are pulling and being pulled. And all of them are visible. They are made of galaxies. Galaxies emit light. We can see them, photograph them, measure their redshifts, catalogue their positions. However hard they were to find, however thick the dust that hid them, they are ultimately things that glow, matter that shines. But matter that shines is only a fraction of what exists. The galaxies we see are not the whole story. They are not even most of the story. They are the glowing embers sitting on top of a much larger, much heavier foundation. A foundation that does not shine. And a scaffolding that holds everything in place but never announces itself with a single photon. Everything we have mapped, everything we have named, everything we have measured as it pulls us through space is just the portion of the universe that happens to be visible. The rest is dark. Everything we have described so far. The Norma cluster, the great attractor region, the Vela supercluster, the Shapley concentration, all of it. Every structure we have named, every mass we have measured, every gravitational engine we have identified pulling us through space. It is only the visible portion. There is more, so much more, and we cannot see any of it. Take a breath. What comes next requires a shift in perspective. Everything we have discussed until now has been matter that glows. Galaxies emit light. Stars burn. Gas clouds fluoresce. Even when dust blocked our view, we found ways around it. Infrared, radio waves. We peered through the murk and found what was hiding there. Those discoveries felt like victories. Each new supercluster, each hidden concentration of mass felt like another piece of the puzzle falling into place. But the puzzle is not what we thought it was. Ordinary matter. The stuff that makes stars. The stuff that makes planets. The stuff that makes you. It accounts for only 5% of the universe. 5%. That is everything. Every galaxy we have ever photographed. Every nebula we have ever named. Every black hole we have ever detected. All of it together represents 1/20th of what exists. 27% of the universe is something else entirely. Something that does not emit light. It is not dark the way an unlit room is dark is not dark the way an unlit room is dark. It is dark the way a thought is dark. It has no color, no surface, no form we can perceive directly. It is invisible in the most absolute sense of the word. We know it exists because of what it does. Galaxies spin too fast. If you add up all the visible matter in a spiral galaxy, all the stars and gas and dust, and calculate how fast the outer edges should be rotating, you get one number. When you measure how fast they actually rotate, you get a different number, a much higher number. The outer stars are moving so quickly that they should fly off into intergalactic space. Now, they should have left their galaxies behind long ago, but they do not. Something holds them in place. Something we cannot see. That something is dark matter. It wraps around galaxies like an invisible cocoon. It extends far beyond the visible edges, forming halos that dwarf the starry disks we photograph. The Milky Way is not just the band of light you see on a clear night. It is embedded in a sphere of dark matter that stretches much farther than any star. We live inside a shell we cannot perceive, but dark matter does more than surround individual galaxies. It connects them. Imagine a spider web, not a flat web pressed against a window, but a three-dimensional web filling a room. The silk strands stretch in every direction, crossing and intersecting, forming a complex lattice. At each junction, where multiple strands meet, there is a droplet of dew. The web itself is nearly invisible. The droplets catch the light. The cosmic web works the same way. Dark matter forms the strands, vast filaments stretching across hundreds of millions of light years, invisible threads connecting one region of space to another. And at the junctions, where these filaments meet, where the dark matter is densest, ordinary matter collects. It falls into the gravitational wells that the dark matter creates. It forms galaxies. Those galaxies clump together. They become clusters. They become superclusters. The droplets are what we see. The web does the heavy lifting. Consider scaffolding around a building under construction. You look at the structure and you see windows, floors, the glass and steel that will eventually become offices or apartments. What you might not notice is the scaffolding itself, the temporary framework that holds everything in place. The building could not stand without it. The windows would collapse. The floors would crumble. But once the building is complete, the scaffolding comes down. It was essential, but invisible in the final product. The visible universe is the windows. Dark matter is the scaffolding. Every supercluster we have named sits at a node in this web. The Great Attractor region is not a random concentration of mass. It is a junction, a place where dark matter filaments intersect. Galaxies poured into that intersection over billions of years, following channels they could not see. Vela is another node. Shapley is another. Laniakea is not just a supercluster. It is a watershed defined by dark matter topology. Computer simulations have mapped this structure. Programs with names like Illustris, T, NG model the evolution of the universe from its earliest moments to the present day. They track how dark matter clumped and stretched and collapsed under its own gravity. They show filaments forming like frost spreading across a window. They show voids opening up between the filaments, empty spaces where dark matter is sparse and galaxies never form. And they show nodes brightening as ordinary matter falls in, condensing, igniting into stars. The simulations match what we observe. The distribution of galaxies across the sky follows the pattern the dark matter models predict. We see the nodes, we infer the web, but there is still more we cannot see. 68% of the universe is something even stranger than dark matter, dark energy, a force that pervades all of space and pushes everything apart. We will come to that. For now, consider the numbers. 5% ordinary matter, the stuff we can see. 27% dark matter, the scaffolding we cannot see. 68% dark energy, a force we can only measure by its effects. We have built our entire map of the universe from that 5%. All our telescopes, all our surveys, all our careful measurements of redshifts and velocities and distances. We have been studying the droplets on the web, the glowing nodes at the intersections of filaments we cannot perceive. We have charted the windows and ignored the scaffolding. What pulls our galaxy through space is not just the visible mass. It is the dark matter underlying it, the filaments that connect the nodes, the cosmic web that shapes the flow of everything. The structures we can see are riding on structures we cannot. Passengers on a current that has no light. That current has no light, but it has something else. Time. The flow we have been describing did not begin when humans first looked up. It did not begin when the first fish crawled onto land. It did not begin when the first star ignited in the Milky Way. It began almost immediately after everything began. The universe is roughly 14 billion years old. That number exists in textbooks and documentaries. We hear it and nod, but 14 billion years is not a number anyone can feel. It sits outside the architecture of human intuition. Try anyway. 14 billion years ago, there was no structure, no galaxies, no clusters, no superclusters, no web, just a dense fog of particles expanding outward from a single point. Within that fog, gravity started its patient work. Regions slightly denser than their neighbors began pulling matter inward. The first threads of the cosmic web started forming. The flows we have measured with our telescopes are not new. They are not recent developments in an old universe. They have been operating since the beginning. The current that carries our galaxy toward the Norma cluster, toward the concentration of mass in the southern sky, has been running for nearly the entire history of existence. We are watching something that started before there were eyes to watch anything. Imagine a cathedral, not a church, a cathedral, the kind that takes generations to build, stone by stone, arch by arch, and the workers who lay the foundation know they will never see the spires completed. Their grandchildren might not either. The building rises over centuries. The cosmic web is that kind of construction project, except the timescale is not centuries. It is billions of years. The foundation was laid 14 billion years ago, in those first moments when gravity began sorting matter into threads and nodes. The walls are still going up. The structure is still forming. No one who sees the beginning will see the end. The universe, it turns out, is very good at hiding things from us. It hid the Norma cluster for most of human history. It hid Vela until 2014. It hid the entire concept of dark matter until the 20th century. I am starting to suspect the universe enjoys being mysterious. Hell, but time might be its greatest hiding place. Our galaxy moves at 1.3 million miles per hour toward the structures we have been describing. That sounds fast. It is fast by any human measure. A bullet seems slow by comparison. A rocket seems stationary. But consider the distances involved. The Shapley supercluster lies 650 million light-years away. At our current velocity, traveling without pause, without slowing, without deviation, it would take hundreds of billions of years to reach it. Not millions, not billions, hundreds of billions. The universe is 14 billion years old. The journey to Shapley would take more than 20 times longer than the universe has existed. Let that settle. The cosmic flow is a river so vast and ancient that even the riverbanks are moving. And the landscape itself changes over the time it takes the water to flow. Stars are born and die. Galaxies merge and reform. New clusters condense from the filaments of the web. By the time anything reaches its gravitational destination, the destination itself has transformed. We are not passengers on a fast train. We are passengers on a glacier. The movement is real. The direction is measurable. But the arrival is beyond comprehension. This reframes everything. In 4 billion years, our galaxy will collide with Andromeda, our nearest large neighbor. The spiral arms will interpenetrate. 200 billion stars from one galaxy will pass through 200 billion stars from another. That sounds violent. It sounds like destruction, fire and chaos, and the end of everything we know. It will not be like that. And here is something that surprises most people when they first hear it. When the Milky Way and Andromeda collide, almost nothing will actually hit anything else. The space between stars is so enormous, so incomprehensibly empty, that two galaxies can pass directly through each other without a single stellar collision. Picture two clouds of gnats. Each cloud contains billions of gnats. The clouds drift toward each other and merge. Do any individual gnats collide? Almost certainly not. The gnats are tiny. The space between them is vast. The clouds simply intermingle. That is what will happen to our galaxy in 4 billion years. The gravitational fields will interact. Orbits will change. Stars will be flung outward or pulled inward. The shapes of both galaxies will distort beyond recognition. Over hundreds of millions of years, and they will settle into a single, larger structure. Astronomers have already named this future galaxy Milkdromeda. The Milky Way plus Andromeda merged into one, but the individual stars will not touch. They will simply be rearranged, like cards shuffled in an infinitely slow hand. We are watching the construction of enormous cosmic structure in real time, but real time, at these scales, means billions of years. The merger with Andromeda is a single event in a process that spans the age of the universe many times over. The flows continue. The web keeps forming. Matter keeps falling toward the densest nodes, and all of it happens so slowly that civilizations rise and fall in the pause between heartbeats. Every empire humanity has ever built could fit inside a single second of cosmic time. Every war, every monument, every poem written, and every city abandoned, all of it happens in a duration the universe does not notice. This is not tragic. It is simply the nature of deep time. The flows that carry us predate everything we know. They will continue long after our sun expands and swallows the inner planets. They will continue after the last red dwarf stars exhaust their fuel and go dark. The current runs deeper than any single galaxy, any single life, any single moment of awareness. We are part of something patient, something that does not hurry because it has nowhere else to be. The web builds itself over eons. The rivers of gravity carve their paths across distances that light itself needs millions of years to cross. And none of this will affect your life tonight. None of it will hurt you. Everything we have described. Yet the gravitational pull of structures so massive they bend the motion of 100,000 galaxies. The invisible web of dark matter stretching across the observable universe. The voids pushing from behind. The superclusters pulling from ahead. The relentless drift towards something hidden behind a wall of stars. None of it will touch your life. Not today, not tomorrow, not during the lifetime of anyone you will ever meet. Not during the lifetime of anyone they will ever meet. The timescales are simply too vast. The distances too enormous. The motion, despite its speed, too gradual to perceive. You woke up this morning. You made coffee, or tea, or nothing at all. You checked the weather. You thought about what the day might hold. And during that entire time, from the moment you opened your eyes until now, our galaxy drifted 31 million miles closer to a gravitational basin we cannot see. You felt nothing. No acceleration pressed you into your mattress. No vibration hummed through the walls. No wind rushed past the windows as the planet hurtled through space at speeds that would turn a spacecraft to vapor. The coffee sat still in its cup. The surface of the liquid remained flat and calm. Not a ripple. That is the strange gift of cosmic motion. It is invisible to those inside it. Consider what you are right now. You are standing on the surface of a planet. That planet is orbiting a star. That star is orbiting the center of a galaxy. That galaxy is orbiting a local group of dozens of other galaxies. That local group is flowing within a supercluster 500 million light-years wide. And that supercluster is falling toward a gravitational basin anchored by structures we discovered only in the last decade. Layer upon layer of motion. Orbit within orbit within orbit. And none of it registers. Not in your muscles. Not in your inner ear. Not in any instrument small enough to fit in your hand. The universe is rushing around you at 1.3 million miles per hour, and your morning proceeds exactly as it would if everything were perfectly still. This is not a failure of your senses. This is physics being kind. Motion is only perceptible relative to something nearby. When you sit in a car traveling smoothly down a highway, you feel stationary. The cup holder stays put. Your hands rest easy on your lap. You only feel the motion when the car accelerates, or brakes, or turns. And constant velocity feels like stillness. Now imagine a vehicle so large that everything around you moves with it. Not just the seat beneath you, but the road, the countryside, the horizon in every direction, the air itself. If everything moves together, there is nothing to measure against. No reference point to reveal the speed. That is our situation. The entire observable universe around us is embedded in the same cosmic flow. The nearby stars, the neighboring galaxies, the dust clouds and the voids, all of it drifts on the same current. We are passengers on a vessel so vast that the deck never tilts, the hull never creaks, and the stars outside the window appear frozen in place. They are not frozen. They are racing alongside us. And because they keep pace, they seem still. The constellations will not change tonight. And they will not change next year. They will not change during your entire life, or during the lives of your children, or their children, or 100 generations beyond them. The patterns you see when you look up at the sky will look almost exactly the same as the patterns your most distant descendants will see. Orion's belt will still hang in the winter sky. The Big Dipper will still point toward the north. Scorpius will still arc across summer evenings. The shapes will hold. The stars will appear fixed. The sky will seem eternal. It is an illusion, of course. Over tens of thousands of years, the constellations will distort. The stars will drift apart or closer together. Familiar shapes will become unrecognizable. But tens of thousands of years is a timeline no human mind can grasp as lived experience. For every practical purpose, So for every night you will ever spend looking upward, the stars are permanent. This is not cosmic accident. This is the mathematics of distance. The stars are so far away that their apparent motion shrinks to nothing on human timescales. Even the fastest moving stars in our sky shift by tiny fractions of a degree each century. Your eye cannot detect it. Your camera cannot capture it without decades of comparison images. The sky appears frozen because the gaps between us and those distant suns are simply too enormous to cross in any meaningful human time frame. The same applies to the galaxies pulling us. The same applies to the voids pushing us. The same applies to everything we have described across this entire journey. The motions are real. The forces are measured. The drift continues every second. And yet, none of it breaks through into daily experience. Your coffee will stay still in its cup tomorrow morning. There is something profound in this. The universe contains violence on scales we cannot comprehend. Stars explode. Galaxies collide. Black holes swallow light itself. Matter falls across distances that take millions of years to cross, even at the fastest possible speed. And here, on the surface of one small planet, life found a pocket of stability. Not stillness, stability. The difference matters. We are not motionless. We are embedded in motion so smooth, so consistent, so free of turbulence, that it might as well be stillness for everything that matters to a beating heart. The universe is in motion. You are in motion. Your planet, your star, your galaxy, your supercluster. All of it rushing through the cosmic web at speeds that make our fastest rockets look like drifting leaves. And somehow, against all of that, breakfast happens. Conversations happen. Sleep happens. Children learn to walk on a floor that feels perfectly solid, while the entire system screams through the dark at over 1,000,000 miles per hour. The flow will continue. Long after your life, and after every life currently breathing on Earth, the current will carry this galaxy toward whatever waits at the center of that gravitational basin. The merger will happen. The structures will shift. The universe will keep building itself across timescales that dwarf the age of our entire species. But you will not be here to worry about it. Neither will anyone else alive today. Neither will their grandchildren, or 1,000 generations of grandchildren after that. The timeline is so vast that it exists in a different category from human concern. It is not a danger any more than the eventual cooling of the sun is a danger. It is simply the background hum of existence, too slow to matter, too distant to fear. What remains is something simpler, something quieter. You are part of an ancient current. You are made of matter that has been falling toward dense regions since the first structures formed. You carry the momentum of billions of years in every atom of your body. And tonight, when you rest, the flow will continue around you, beneath you, through you, without disturbing a single dream. The universe moves, and you are still enough to notice. But notice what, exactly? We have traced currents and named structures. We have mapped superclusters and measured velocities. We have peered through dust and detected signals from regions hidden for centuries. And still, after everything, the map remains incomplete. There are things we do not know, not small things, not minor details waiting to be filled in by the next telescope or the next survey. Fundamental gaps, missing pieces that might reshape everything we think we understand about why we move and where we are headed. Start with the flow itself. We measure our galaxy's motion against the cosmic microwave background. That ancient light gives us a reference frame, a stillness against which we can track our drift. And for decades, astronomers assumed the structures we found explained the motion. The Great Attractor, the Norma Cluster, Vela, Shapley. Each discovery added another piece to the puzzle, another mass pulling us through space. But here is the problem. When researchers map the velocity of galaxies across even larger volumes, they find something troubling. The flow does not stop at Shapley. It does not settle into the gravitational well we mapped. Instead, there are hints of a larger current beneath the current, a deeper pull operating on scales we have barely begun to measure, 3 billion light-years away, perhaps further. Something may exist that we have not yet seen, something that makes Shapley look modest, a structure so massive that it draws not just our galaxy, not just our supercluster, but entire swaths of the observable universe toward it. Yet we call this evidence the bulk flow, a coordinated motion of matter across hundreds of millions of light years that suggests our local region is itself falling towards something far more distant. We do not know if this structure exists. We cannot see it directly. The measurements are at the edge of our precision. The error bars overlap with other explanations, but the signal persists. Multiple studies, multiple techniques, multiple teams. They keep finding motion that exceeds what the known structures can produce. Imagine you are on a raft drifting down a river. You can see the banks. You can feel the current. You understand why you move. Then someone tells you that the entire river is flowing downhill toward a waterfall you cannot see. A waterfall beyond the horizon, beyond the fog, and beyond even the sharpest bend you have managed to glimpse. You would want to know if that waterfall exists. You would want to know how far away it is. We are in that position now. We have charted most of the sea. We have named most of the islands. But directly behind the galactic center, in the thickest part of the fog, there is a region where the map is still blank, and that blank region might contain the most important piece of the entire puzzle. 10% of the zone of avoidance remains completely opaque. Infrared cannot pierce it. Radio waves scatter and fade. Every technique we have developed hits a wall at the densest part of the galactic plane, right where we need to look most urgently. Our map of the local universe is a map with 10% of the territory still marked here be dragons. And those dragons might be real. We know massive structures hide in that direction. Vela was found there. The densest part of the Great Attractor region sits there. Every gravitational model suggests that more mass waits in precisely the region we cannot observe. But we are guessing. We are inferring shape from shadow. We are tracing the outline of something we cannot directly see. The cosmic microwave background offers another clue, and another mystery. There is a region in the southern sky, roughly 13 degrees across, where the microwave light appears slightly colder than the surrounding background. Not much colder, just a fraction of a degree, but consistent, persistent, strange. Some researchers believe this cold spot marks the location of an enormous supervoid, a region of space emptier than the already empty average, emptier by a margin that stretches credibility. A void potentially billions of light years away, so vast that light crossing it loses a measurable amount of energy. The cold spot might be a window into the largest absence of matter we have ever detected. Or it might be something else entirely. Statistical noise, an artifact of our instruments, a feature we do not yet understand. This is where the science lives, not in the answers, but in the questions we cannot yet resolve. And beneath all these specific mysteries lies a deeper puzzle. The cosmological principle states that the universe should look roughly the same everywhere on sufficiently large scales. No special locations, no preferred directions, smooth and uniform when you zoom out far enough. But our corner of the universe does not look smooth. Laniakea is unusually massive. Shapley is unusually concentrated. The density of structure in our region exceeds what standard models predict for a typical patch of space. We appear to live in an outlier, a statistical anomaly, a corner of reality that is denser, more organized, more gravitationally active than the cosmic average. Not an ending, not a destination, a process still unfolding. Perhaps we are simply lucky. Perhaps our observations are incomplete. Perhaps the models need refinement. Or perhaps there is something about our location that we do not understand. Something that selected for complexity. Something that allowed structure to grow here in ways it did not grow elsewhere. We do not know. That phrase should comfort you rather than frustrate you. We do not know means the story continues, and it means there are discoveries waiting. It means the universe still has secrets to offer anyone willing to look. The fog will thin eventually. New instruments will come online. New techniques will push deeper into the opaque regions. The blank spaces on the map will fill in, one pixel at a time, over decades and centuries of patient work. But for now, we sit with the uncertainty. We accept that the forces shaping our motion may trace back to structures we have not yet named. We acknowledge that the biggest piece of the puzzle might hide in precisely the region we cannot see. This is not failure. This is the nature of exploration at the edge of the known. Every map has margins. Every model has limits. The universe does not arrange itself for our convenience. What we know is vast. What we do not know may be vaster still. And somewhere out there, beyond the dust, beyond the fog, beyond the limits of our sharpest instruments, The truth waits, patient, ancient, indifferent to whether we find it tonight or in 1,000 years. The truth waits. That phrase hangs in the darkness between us and the unseen structures that shape our path. But perhaps we should linger here a moment longer, not on what we cannot see, on what we have become while looking. We are moving. We have always been moving. Before the first cell divided in the primordial ocean, before the earth cooled enough to hold liquid water, before our sun ignited from its collapsing cloud of hydrogen and dust, this motion was already ancient. The cosmic current we ride began flowing when the universe itself was young, when gravity first sorted matter into streams and eddies that would eventually become the scaffolding of everything. Our entire species has existed for less than 0.002 of 1% of the time this flow has been operating. Think about that ratio. If the cosmic migration were a single year, humanity would occupy the final 4 minutes before midnight on December 31st. Not the final day, not the final hour, the final 4 minutes. And in those 4 minutes, we woke up, we looked around, we started asking questions. The galaxies do not feel the pull. Consider that for a moment. The Norma cluster does not know it is massive. Shapley does not know it dominates the gravitational landscape of the local universe. The filaments of matter threading through the cosmic web do not sense the flows that define them. In every structure we have mapped, every attractor we have named, every void whose absence shapes the current, all of it operates in perfect unconsciousness. There is no awareness out there, only physics, only matter responding to curvature, only the blind arithmetic of gravity playing out across scales that dwarf imagination. Except here, on a small, wet rock orbiting an unremarkable star in an unremarkable arm of an unremarkable galaxy, something happened that might be genuinely extraordinary. Matter organized itself into patterns complex enough to become aware of the patterns. Carbon and oxygen and nitrogen and hydrogen arranged themselves into structures that could ask where they came from and where they were going. We are part of a migration whose participants do not know they are migrating. Every galaxy in Laniakea, every cluster falling toward Shapley, every supercluster responding to the push and pull of cosmic structure. None of them know, none of them wonder, none of them look up at the night sky and feel awe at what they see. Only us, only here, only now. The ability to map our own cosmic motion might be the rarest phenomenon in the universe, rarer than superclusters, rarer than voids spanning hundreds of millions of light years, rarer than the delicate filaments of dark matter that web the cosmos together. Intelligence capable of noticing that it is moving, of naming the forces acting upon it, of feeling something, anything, when confronted with scales beyond imagination. We do not know how rare consciousness is. That remains one of the deepest open questions in science. But consider the silence. Yet we have listened for signals from other minds for decades. Radio telescopes pointed at thousands of stars, algorithms searching for patterns in the noise, and so far, nothing. Perhaps we are early. Perhaps we are looking in the wrong places. Perhaps the universe teems with life that simply does not communicate in ways we recognize. Or perhaps the emergence of awareness is so improbable, so dependent on conditions so specific that it happens almost never. Perhaps most galaxies flow through the cosmic web for their entire existence without ever producing a single mind capable of asking why. We do not know. That is the honest answer. And that is one of the most exciting sentences in modern science. The map is incomplete, the story is unfinished, and there is still so much to find. But what is hiding in that final 10% of the zone? What structures lurk in the regions our instruments cannot yet penetrate? What forces might we discover when we finally see clearly into the blind spots that have obscured our view for so long? We do not know. We do not know. We do not know. But we are asking. That matters. The asking matters. The universe does not notice us. It cannot. There is no mechanism by which the cosmos could register our presence or care about our fate. We are a side effect, an accident, a brief flutter of complexity in a vast expanse of simple physics. The stars will continue to burn whether we watch them or not. The galaxies will continue to fall whether we map their trajectories or not. The cosmic migration will proceed toward its unknown destination with or without witnesses. And yet the witnessing transforms something. Not the universe. Us. To know that you are moving at more than 1,000,000 miles per hour through the fabric of space itself. To understand that your motion results from gravitational structures larger than your mind can truly comprehend. To grasp, even partially, the immense architecture of matter and emptiness that surrounds you in every direction. This knowledge changes what it means to be human. It places you in context. It reveals your position in something vaster than ancestry, vaster than history, vaster than the whole of Earth's existence. You are not stationary. You are not central. You are not unique. You are a passenger, a brief pattern, a momentary configuration of atoms that happens to be capable of knowing where those atoms are heading. That might be enough, and that might be everything. The terror of the unknown can become something else if you let it. Not comfort exactly, something closer to anticipation. The blank spaces on the cosmic map are not threats. They are invitations. Each obscured region represents discoveries waiting to be made. Each mystery represents a door that has not yet been opened. We are going somewhere. We do not know where. But for the first time in cosmic history, something in the universe is asking the question. Something massive is hiding behind the Milky Way, and it is getting closer. You have heard those words before. At the beginning, they carried weight, perhaps a thread of fear, the unknown pressing against the edge of your awareness. A force you could not see, dragging everything you have ever known toward a destination no map could show. But now you have traveled with us, through the dust, past the wall of light that separates what we can see from what we cannot. You have felt the pull of Norma, the hidden bulk of Vela, the immense gravity of Shapley reaching across 650 million light-years to bend our path. You have traced the scaffolding of dark matter that holds everything together. You have learned that we are being pushed as much as pulled. And the words mean something different now. Something massive is hiding behind the Milky Way. Yes, it is, and it always will be. The universe has not finished deciding what happens next. Will Laniakea eventually merge with Shapley? Will these two great congregations of matter drift together across the coming eons, combining into something even more vast? Or will dark energy continue to stretch the fabric of space faster than gravity can close the gap? No one knows. The answer lies billions of years in the future. The equations balance on a knife edge. The outcome depends on forces we have only begun to measure, on physics we have only begun to understand. And that is beautiful. A question the cosmos itself has not yet resolved, a story still being written in the slow drift of superclusters through the void. Since this journey began, since you pressed play and settled into the dark, our galaxy has crossed 31 million miles. It happened without sound, without sensation, without disturbing the stillness of wherever you are now. That motion has been happening for 14 billion years. It will continue for trillions more. The destination remains unknown, and it may always remain unknown. But here, tonight, on a small, wet world, circling an ordinary star in the outer suburbs of an unremarkable galaxy, something extraordinary is happening. You noticed. You are made of atoms forged in the hearts of dead stars, arranged, briefly, into a pattern that can wonder, that can ask questions the universe never thought to pose, that can feel something like awe when confronted with the scale of its own insignificance. The terror has transformed. The hidden pull is no longer a threat. It is a gift, to exist at all, to exist now, to be aware, even for a moment, of the immense and ancient current that carries us all. The destination is unknown. Let it stay that way. Something massive is hiding behind the Milky Way, and we get to be the ones who noticed.